Hello everyone, welcome back to Bytes of CSE. So in this lecture, we will be learning about the variance of gradient descent algorithm. So based upon when the parameters are updated in your model, there are three variants of gradient descent algorithm. The batch gradient descent algorithm, stochastic gradient descent algorithm, and mini-batch stochastic gradient descent algorithm. Now, before we move on to each of these types of gradient descent algorithms, let us understand what this parameter updation means. So, what is a parameter here? If you are familiar with MLP, if you have gone through my MLP lecture, or if you are familiar with machine learning, you know that this is the very basic equation of a machine learning algorithm. That is y equals to wx plus b, where y is the output, W is a weight associated with a particular layer or a particular algorithm, and B is the bias, and X is your input. So, if you can recall, this also looks familiar to similar to the equation y equals to mx plus c, which is the equation of a straight line. So in case of deep learning, what we do is, in order to change this straight line into something non-linear curve, we add an activation function like a sigmoid or a hyperbolic tan or ReLU to this. I've also covered the activation functions in this particular channel. So say you're trying to apply sigmoid over here. So you will be taking the output, and in order to convert the straight line to a sigmoid function, sigmoid curve, you will be doing this computation like 1 by 1 plus e to the power minus y. So what I'm trying to say here is, see, no new parameters like a, b, c, d or anything has been introduced in this activation function. It is straight away taking this output and working with that. But in this case, we are using this W and B, which can be changed. Since we have multiplied X to W and we have added this bias, you can in no way change this input X because the input is the input. You can't change it. So in order to make this Y value close or similar to the actual value T, you will need to adjust the values of this W and B. And these W and B, these are known as the parameters in your model. If I have to explain that a bit more clearly, say I project the target on a 2D plane and your target looks like this. The different examples, the different data which I have got from the data set, say I project that to a 2D plane and it looks somewhat like this. The distribution looks somewhat like this. And you have a computer program where if you can input the value of W and B, it will draw a straight line for you. So we start off with a very low value of W and B and your straight line is about here. Now you know that in order to fit in this kind of a distribution, you will need to take your straight line from here to here. So in this case, when we apply an activation function, say at this position, this straight line will change into a curve like this. But even if that curve looks very similar to the actual distribution, it will still not give you the true result because the value starts from here and you are at this position. So the activation function is actually doing the curve fitting, but it is not actually moving the line up here or there. In order to move your line up from here to here, you will need to change the values of W and B. Now in this case, I have projected the value, you know this is a true distribution, and for a particular value of W and B, the straight line is here. Now you accordingly change the values of your W and B till your straight line does not move up to here. So in machine learning perspective, how a machine learning is supposed to do this WB updation? So what it does here, this is where an optimization algorithm like gradient descent comes into play. So say you have started your machine learning has started from this point. Your model has started from this point. Now what it does is it computes the distance between this point and this point. And this distance is actually the error. And your optimization algorithm tries to reduce this error, or in other words, in this diagram perspective, it tries to reduce the distance. So in order to do that, it will need to manipulate the values of W and B, and of course the value of the gradient and the direction of the gradient, like it moves to the opposite of the direction of the gradient, will give it an idea of how to manipulate this position of this line so that it moves up to here. So I hope now this becomes clear that how this error estimation helps in fitting the predicted value to the true value. So your parameters are these W and B. So now we can get down to how this W and B, or rather when this W and B are updated, the variance depend on that. So before we move on to that, a quick idea of what is the error in this case. Now in case of regression, it's very easy because say the house price of this is 470K. This is a true value and your machine learning predicts that this is 40K. So the error is very straightforward. The easiest way in order to determine the error is 470 minus 40K, right? But what about a classification problem? Say you are given, or your model is given this picture which is of a dog, and now it predicts that this is a cat. So now you need to find the error in here. So dog minus cat, how is that going to be like? So what happens here is basically before declaring this to be a cat, your your model tries to compute the probability of this being a dog and the probability of this being a cat. Say all the images, like it has been trained, or the training process is going on only on the images of dogs and cats. So there are just two categories, dogs and cats. So it finds the probability of this being a dog and it says that I am 0.4 sure that this is a dog and I am 0.6 sure that this is a cat. And since 0.6 is greater than 0.4, it concludes that this is a cat. But what should have been the true probabilities at this position? Since this is the picture of a dog, this probability should have been 1. And this is not a cat, therefore this PC should have been 0. Now I think you have an idea of how error is calculated in case of classification problem. I will do a video on this later. So now let's focus on what this lecture was all about. So first we will be dealing with batch gradient descent. So in batch gradient descent, suppose you have a data set and you have 506 examples in this data. So for each example, you will calculate the error. Then you will calculate the gradient and you will store that. And after you have gone through all those examples, you will compute the average gradient. And based on that value, you will update the parameters. If I have to mathematically express that, the average gradient will be this. Let us decode what it means. So we will start from the innermost bracket or the innermost function. In this case, this is this one. So for a particular example I, where the model has predicted that this is Pi, whereas the true value is Ti, you will calculate the error, and on that error, you will calculate the gradient Gi for that example. So this is this part. And now, in order to compute the average gradient, you will sum up all the gradients you have stored for all the examples, and you will divide that by the number of examples. So this is your average gradient. And using this average gradient, you will update the parameters as theta, where theta is your parameter, is equals to theta minus learning rate into average gradient. Now, if you have gone through the gradient descent algorithm lecture, you are familiar with this equation also, where in case of theta, I have used a term x, and this gradient was expressed as f prime x or nabla x. So what might be the problem with your batch gradient descent algorithm? There might be some problem, otherwise you wouldn't have two more variants of this gradient descent algorithm. So the first thing is that the parameters are updated only after going through all the examples. That is, after your model goes through all the examples, it will update the parameter once. Now, if you have gone through the video on gradient descent, you know I've discussed there that you actually have to take very controlled steps to move to the minima, or the point where the error is minimum. Otherwise, you will just move away. If you take a sharper or a steeper step size, you might miss this point. So like when you are taking very small step size, what would that mean? You will have to update the parameters a number of times. So if say your dataset contains say 30,000 examples or 40,000 examples, which is very common in case of deep learning or machine learning too. So this process will be very slow. So the first problem is slow convergence. I'm sorry, actually I had written this f prime x, so it's kind of, this is actually slow convergence. Next, see, you are storing the gradient for all the examples. So for that, you will be needing a substantial amount of memory to store the gradient, because you have to compute the average of that. And if the number of examples are too high and the feature dimension is also very, there is a number of features also quite large, the amount of memory needed to store that will also be very high. And in my practical experience, I have actually seen memory running out. So that's a very big problem. Also, in order to update the parameter, like this is a serial process. You can't parallelly compute you can parallelly update the parameters. So in this case, there is no parallelizability is not possible in case of batch gradient descent, and in fact all of these makes it very less suitable for big data applications. It also has another limitation which I will be talking about shortly. So let's move on to stochastic gradient descent. So obviously you know that this stochastic gradient descent came in to address the problems of your batch gradient descent. So how the algorithm works here is, for each example now, you will calculate the error, calculate the gradient, and you will update the parameters. So if your dataset contains 500 examples, so after the model goes through all the 500 examples, in case of your batch gradient descent, it will update the parameter only once. But in case of stochastic gradient descent, by the time your model goes through all the examples, it will have updated the parameters for 500 times. So definitely the convergence is much faster, and also you are not storing the gradient. Therefore, it is also computationally efficient, and also it is parallelizable. So if I have to mathematically express that, so here you're not storing any gradient, you're not doing any average. So you are finding the error for a particular example, finding the gradient, and using that gradient, you are updating the theta or the parameters, or that is your W and B. So as I said, it's computationally efficient, and also it is very suitable for online learning. What is online learning? Now, online learning is where your model accepts a new data and updates a parameter accordingly. So whenever a new data comes in, the model updates itself. So this is possible in case of stochastic gradient descent, but in batch gradient descent it is not easy to implement this thing. So batch gradient descent is therefore not very suitable for online learning. But what might be the problem with your stochastic gradient descent? Because you have another variant. So of course this has to have some problem. See, your dataset will contain outliers. This is very common to have outliers, and without outliers, your model won't be very robust or very stable. So, in case of outliers, this error value will be greater, and also the gradient value will be quite different from what the gradient should have been. And since immediately your parameters are getting updated, your parameters might diverge, in worst case might diverge from the true solution. So when an outlier is encountered, the computed gradient for this particular example can be large, which would lead to a significant update. So if this is very large, so learning rate into gradient, this will also be large, or at least it will be very different from the other examples. So this will result to the models overreacting to the outliers and potentially diverging from the optimal solution. So in a few words, if I have to say, I'll say that this is very much sensitive to outliers. Now this is a big problem. But these are extremely important too. So this sensitivity to outliers was not quite a problem in case of batch gradient descent, because we were averaging the gradient. So there won't be many outliers in your data, because if there are many outliers in your data, your model will actually learn nothing. So there will be a few outliers, and since we are taking the average value of the gradient won't vary much. For a few larger values, it won't affect much. But this is going to be a big problem in this case of a stochastic gradient descent. But stochastic gradient descent also provides some very good benefits. So in order to address this problem, we took a middle path which is known as the Minibatch stochastic gradient descent algorithm. So here what we did, suppose there are 500 examples. So what we did was we divided these examples into batches of 10. So now your data set contains 50 batches of data. So each of this batch, whenever the gradient of a batch is calculated, the parameters are updated. So the equation looks like this. So this is a cross between the the batch gradient descent and the stochastic gradient descent. So here what happens here is we calculate the error of each example in a batch, and we find the gradient of each example in that batch, and we find the average gradient of that batch, which is I have shown as mini batch gradient. So just to show you the difference, so we started off with say 500 data examples. In case of your batch gradient descent, after the model will go through 500 example, it will update the parameter once. In case of stochastic gradient descent, after the model has finished going through 500 example, the parameters will be updated for 500 times. But in case of mini-batch stochastic gradient descent, since we are considering that we have broken down this data set into batches of 10, and each batch, after after the gradient of one batch is computed, the parameters are updated. So after the model has gone through these 500 examples, the parameters will be updated for 50 times. So it's a middle path. It does not converge as fast as a stochastic gradient descent, but this is not as slow as the batch gradient descent. And the added advantage is it is also a bit more robust to outliers than this stochastic gradient descent. So, and since we are taking small batches, so the amount of memory needed to store the gradients will also not be large. So the memory requirement is within limits, not too much like the batch gradient descent. So now for each batch, after going through one batch, the W and B, that is the parameters, will be updated. Now this is a beautiful, this particular equation is wonderful, because if you only remember this equation, you will not have to remember separately the batch gradient descent, mini batch, or the stochastic gradient descent, because when the value of your B is equals to 1, this becomes a stochastic gradient descent. When the value of B is equivalent to the number of examples in your data set, it becomes a batch gradient descent. And when the value of B is in between 1 and the number of examples, that is n, it becomes a mini batch gradient descent. So if you remember only this equation, you will be able to derive stochastic and batch gradient descent. So now, in order to sum up, in case of computational efficiency, batch gradient descent is truly an evil, stochastic gradient descent is best, and mini batch, of course, is not as great as SGD, but also not as bad as BGD, so it is okayish. In case of parallelizability, this is not parallelizable, or it's very difficult to parallelize this. Actually, it is not parallelizable, sorry. Stochastic gradient descent is parallelizable, and this is also parallelizable. In case of online learning, this is again a devil here, whereas both stochastic and mini batch, it supports online learning. In case of robustness to outliers, now this is best. This can't be beaten by these two. This is clearly a devil, and this is okay. So this is actually an okay for all the parameters which are very important in case of very important case of an optimization algorithm. So in most of the cases, we actually use this mini batch stochastic gradient descent algorithm in order to optimize. So that is all for today. So hope you have found this video useful, and thank you for watching.